Alright, in this video we're going to talk about induction. And to start talking about induction, we're going to need to introduce a few terms and concepts to you. So the first one is the Weber, or the flux. So this is a unit of flux, so this is flux. And the unit is the Weber. I might think that says Weber, but it's pronounced Weber. And the unit looks like a WB. So that's the unit of flux. Now, flux is just an indication of the amount of lines that are in a magnetic field. So here's your magnetic field lines. Might be going from north to south, like in a standard kind of thought process for magnetic fields. So the flux indicates the amount of, almost like the amount of field lines you've got here. But flux, more often than not, is defined like this. That flux is equal to the flux density times by the cross-sectional area. So the flux density is literally a unit. That is the flux density, and that's measured in Teslas. Okay, Tesla. Because Teslas is a unit of flux density, it is also a unit of magnetic field strength. It's a nice indication of magnetic field strength. Because if you think about it, we can define flux density by rearranging this equation as B is equal to flux per unit area. Well, think about that. I've already said that these lines are the flux. And then my unit area is like this area here that this passing through. And so if I was to increase the flux density, I would be increasing the number of lines of flux that was passing through the same area. I increase the number of flux through the same area. I increase the magnetic field strength. It's just an indication that these are terms that are very similar to what you may have come across before, especially in electric fields, because this is the same thing. So in an electric field, you have when you show an electric field or a gravitational field, the closer the lines are together, the stronger the field is. Same thing here. Closer lines together, stronger field. So this term here, like I said, I don't really like this definition of flux because you're defining it in terms of something that it already is. So flux density times by the area. But that's generally what they like to hear as a definition for flux. But there's more to this equation than meets the eye, really, because depending on the area that you're looking at depends on, you actually add what's called a cos theta term in here. Now, if we look at it from the point of view of this scenario here, the area that I'm taking, a circular area that's with this flux incident on it, well then what you'll notice that this is a maximum value. And as you'll notice, cos theta, so that's either going to go between 1 and 0. So obviously in this orientation, you're going to have cos is equal to what, cos theta is going to be equal to 1 in this scenario because it's the maximum. I've got the maximum flux passing through that area in this example. So cos theta, so bear in mind that when you do cos of 90, you get 0, and cos of 0, you get 1. So I'll just remind you of that there. So cos of 90 degrees, you get 0, and cos of 0, you get 1. So that means there's an angle in here that's equal to 0 that we need to be considering. Now, what is the angle that's 0? Well, it's the angle between this and the line that's normal to that point. So you could almost take it as an angle from so there to there. So you can see the angle between those two lines is 0. But what happens if I change the area that I'm interested in? So let's draw that on here. So I'm going to draw a different area now. Let's draw in a different color. So let's draw it like this. See, I rotate that area around. Well, notice what happens is I've rotated that area. What have I lost? I've lost this flux line and I've lost this flux line down the bottom here. And notice that the angle has changed, the area that's incident, that the flux is passing through there. So if we look at this from the perspective of an angle, well now we've got an angle theta that's greater than 0. So this theta was equal to 0. This theta is going to be, I don't know, more like 45 degrees. So now we've actually got a value that that is higher than 0, but less than 1. And so as a result, we are going to get a reduced flux. And as you can see, reduced flux. And if we look at it from the point of view of flux density, we would observe the same thing as well. The flux density would also change. So you just need to be aware that we've got the this value here is equal to b times cos a cos theta. And this is your understanding of what flux is and how this cos theta term fits into this equation as well. Now this becomes more poignant when we start talking about induction, because this circle of influence is eventually going to become like a coil of wire. And that coil of wire is what's going to have an induced electric current based on the magnetic field that's moving through it. But there's more to consider here. So that's just a foundational idea about what flux is, what flux density is, and the equation that is normally used to explain it.